Hello and welcome to this next lecture on fundamentals of acoustics. Today we are going to look at wave equation and integral transforms. That is a new topic, but before that I just wanted to mention we have spoken about sound pressure level, which is LP, and sound power level, which is LW, and which to use when in. Okay, so it's situation dependent, depending on what you need to know, but sound pressure, the pressure generated by a source, pressure generated by a source depends on the boundary conditions. What are the conditions on the wall, okay, conditions on the floor, and so forth. It depends, it is not independent of all these, okay. Whereas the power generated by a source is independent of the surroundings. And so is a better indicator, of the nature of the source. Okay, but these measures have their uses. Now let us look at integral transforms. Integral transforms and the wave equation. Okay. So let us see, we have let's look at a string. Okay, let's look at a string. Let's say we have del 2 W by del x square is equal to 1 over c square del 2 W x comma t by del t square, and let us say this is a string that is between these two limits. Okay, so there is a string, we are going to consider a fixed string of length L. Okay, so we write this equation now as c square del 2 W by del x square as del 2 W by del t square. Okay, Now we take a transform of this independent variable. So we said P is equal to x pi over L, okay, and let's call it 1, let's call this 1, okay, and we'll, so then with this what happens is that del by del P is equal to del by del x into del x by del P, okay. So that if I use this transform over here, what I get is pi square c square L square del 2 W P comma T del P square, okay, is equal to del 2 W by del T square P comma T, okay. Okay, so this is L by pi, okay, is L by pi. So del x, just making it clear, del by del x is equal to pi by L del by del P, okay. That's how this pi square by L square comes, is equal to, okay. Now we have pi going from, or P going from in between these limits, okay. So now what we use is Fourier series, Fourier sine series, Fourier sine series. And why do we use a Fourier sine series? Because we are going to use sine n pi x by L as a basis, and this basis at x equal to 0 is 0, and at x equal to L is also equal to 0. N pi x by L is 0. So it fits the boundary conditions, okay. Sine n pi x by L fits the boundary conditions, and they form a good basis, okay. So now we go to the series, sine series. That means what? My W of P comma T is now represented in the form of twice by pi summation n going from 1 to infinity some coefficient sine n pi x by L, okay. So we are not going to write it in terms of x now, we will write it as sine np, okay. Now if we take the transform, okay, if we in here if we now take the transform, that means we have pi square c square, okay, and what is W of n comma t? The forward, how do we go forward? We go forward using 0 to pi Wp of t sine np dp. Okay, because it's finite, these are discrete, okay, but the coefficients are found using an integral, whereas the solution is found using a series. That's exactly like Fourier series. Okay, so now we have to go from the p domain to the n domain. So what we do is we have pi square c square by l square integral 0 to pi del 2 wp comma t by del p square, and we multiply by sine np dp. Okay, and we do the same on the other side, 0 to pi del 2 w p comma t by del t square sine np dp. Okay, so now the left hand side, okay, the left hand side term is let's just take just this part first. Okay, we have integral 0 to pi del 2 wp comma t del p square sine np dp. Okay, now we integrate by parts. Okay, so what we have, let me take it. So we integrate this by parts, so that is equal to del w p comma t by del p sine np 0 to pi minus the integral 0 to pi, which has derivative, integral, sorry, of the first function and the derivative of the second function. Okay, minus n, okay, sorry, n cos np dp. Okay, now sine np at p equal to 0 and p equal to 5 pi is 0, so this term goes to 0. So we have to contend with this term. So if I again continue, I have a minus w of p comma t n cos np plus now an integral 0 to pi, which is w of p comma t into minus n square sine np dp. Okay, and this, the limits are 0 and pi. Now wpt is 0 at 0 and pi. Okay, it's a fixed string, fixed at x equal to 0, x equal to L, or p equal to 0, p equal to pi. So this term again goes to 0, the boundary term. So now what we have is integral 0 to pi del 2 w of p comma t by del p square sine np dp is equal to minus n square integral 0 to pi w of p comma t sine np dp. Okay, so this is the left hand side term. Okay, so now what do we have? we have this had a coefficient in front, pi square c square by L square. Okay, so we bring that in. So what we have is minus n square pi square c square by L square integral 0 to pi w sine, let me keep the p comma t sine np dp is equal to, I am switching the order of the operators, del 2 del t square integral 0 to pi w of p comma t sine np dp. Okay. Now we are going to define, or we have already defined, the w of n comma t is equal to integral 0 to pi w p comma t sine np dp. Okay. So now what do we have here? We have if we use this definition here, what we have is d2 w n comma t by dt square, which is this term, plus n square pi square c square by L square w of n comma t equal to 0. Okay. Now just I want to mention that this is the forward, we call it the forward process. These are the Fourier coefficients. Okay. And then getting it back is w p comma t is 2 by pi, okay, summation over w n comma t n equal to 1 to infinity sine np. And this 2 by pi comes from the fact that if you do 0 to pi sine np and sine mp dp, okay, then this is equal to 0 when m is not equal to n, and you have 0 to pi sine square np, right. When m equal to n, what do we have? M equal to n sine square np, which is 1 minus cos 2 np by 2 dp, and this integrates to 0. So I get pi by 2. This gives me pi by 2. That is this pi by 2. Okay. So we multiply by 2 by pi before. Okay. And that is why here there is no constant in front. Okay. So now let us see, we are here, okay. So that looks like a harmonic, spring mass equation, spring and mass, okay, mx double dot or x double dot plus omega n square x equal to 0, it looks like that. Okay. So what do we do now? So the solution to this the solution to this is now W n comma t is C1 cos n pi c by L into t plus C2 sine n pi c by L into, we will take L properly, L into t. We could have an exponent solution, but I am taking the sine solution. Okay. So, now we need to deal with the initial conditions. Okay. So, let me just say here we have a string that is fixed at both ends. Those are the boundary conditions. These boundary conditions give us the mode shapes or admissible function sine n pi x over L. Okay. Then we are going to drive it using initial conditions. Okay. But no other forcing, no other forcing. And the boundary conditions are homogeneous boundary conditions. Okay. So, now we have initial conditions which are W for all x at t equal to 0 is W0 of x. Okay. Then the next one, del W by del t for all x at t equal to 0 is equal to W dot 0 of x. Okay. Now, just as we took W p comma t to W n comma t, we have to take W p comma 0 to W n comma 0. Okay. So, along the parallel lines, W now n at t equal to 0 will give a symbol W0 of n, and del W by del t for a single n at t equal to 0 is W dot 0 of n. Okay. Now, what is W0 of n? W0 of n is integral 0 to pi W0 of p okay in terms of p. Okay, this has a form W0 of p also, and this has a form W dot 0 of p also. After all, p and x are related. P is pi x by L. Okay, they are related. So, now W0 of n, first of all, is W0 of p sine n p dp as before, and in terms of x, this is equal to pi by L integral 0 to L this time W0 of xi, which is equivalent to x sine n pi xi by L d xi. Okay. Xi is a dummy variable. Xi is dummy, it could have been x also. X also is okay. Okay. Now, similarly, W0 dot in the transformed variable n is also integral 0 to pi w dot 0 in the p variable sine np dp, or it is pi over L integral 0 to L I am putting xi as the dummy integration variable n pi xi by L d xi. Okay. So, now what do we have? We have to find you have to find C1 and C2. Okay, we have to find C1 and C2. So, what are those? So, now W, if W n of t is equal to C1 cos n pi c by L t plus C2 sine n pi c by L into t, then W 0 n is equal to C2. I am sorry, W 0 n is equal to C1, right. This is nothing but W of n at t equal to 0. Okay. Similarly, W 0 dot of n, which is the same as W dot of n at t equal to 0. If I take the derivative of this, first of all W dot of n comma t is equal to C1 n pi c by L t plus n pi c by L into t C2 n pi c by L into C2. Let me write W dot first. W dot is minus C1 n pi c by L sine n pi c by L t plus C2 n pi c by L cos n pi c by L into t. Okay. Now, if we set W dot n t equal to 0 or W dot 0 of n, then at time t equal to 0 this goes away and I have C2 n pi c by L, or C2 is equal to W dot 0 of n L by n pi c. Okay. So, we have C1 and we have C2. So, my W of n comma t is equal to C1, which is W 0 of n cos n pi c by L into t plus C2. C2 is W 0 dot of n L by n pi c sine n pi c by L into t. Okay. So, we have reached one stage here. Okay. From here we have to get back to W of p comma t, and we have to get back to W of x comma t. Okay. So, we have this expression in the transformed coordinates. Okay. So, we have to get back to WPT, as I said, small w of p comma t, and from there to small w x comma t. Okay. And what is small w p comma t? We said it is a summation 2 by pi summation n equal to 1 to infinity w of n comma t sine np. Okay. So, now we substitute this in here. So, what do we get? We get w of p comma t is equal to 2 by pi summation n equal to 1 to infinity w0 of n cos n pi c by l t plus w dot 0 n l by n pi c sine n pi c by l t into sine np. Okay. And what is w0n? So, let us see. We have 2 by pi, this summation. Okay. w0n is now pi by l integral 0 to l w0 of xi sine n pi xi by l d xi, and we bring it down. Okay, so let us see. This goes and comes here. This goes and comes here. Okay. So, that is this part into cosine n pi c by l t, that is this part, plus okay, pi by l integral 0 to l w0 dot xi sine n pi xi by l d xi into l by n pi c sine n pi c by l t into sine np. Okay, this is small w p comma t. So, what will be w x comma t, small w x comma t, that is given by 2 by l summation over n, okay, cosine n pi c by l t, which is this, then sine n pi x by l, which is this, then integral 0 to l w0 of xi sine n pi xi by l d xi. That is this first term. Okay, I am separating the first term. then plus this pi goes with pi, L goes with L, okay, and I have 2 by pi and NC here. So, I get 2 by pi c summation over n equal to 1 to infinity 1 over n, then sine n pi c by L t sine n pi x by L, which is this fellow, then integral 0 to L w dot 0 of xi sine n pi xi over L d xi. Okay. Now, we had a string which was fixed on both ends, okay, and therefore, the mode shape was sine n pi x by L. Okay. So, rather you would start by A cos k x plus B sin k x and apply boundary conditions, so that you get the mode shape and the eigenvalue k to be n pi by L. Okay. Sin k x is the mode shape and eigenvalue is k equal to n pi by L. But suppose you had a fixed string on one side and free on the other side, or free on both sides. Okay. You would start with the same expression, apply the boundary condition, find the mode shape and the eigenvalue, and that eigen function will sit over here instead of sine n pi x by L, or instead of sine n p. Okay. So, as the boundary conditions change, this basis function changes, or the eigenvalue changes. Okay. So, I will close the lecture here, we will continue in the next class. Thanks.